Welcome to this lecture on dynamic phenomena in insulin-glucose regulation. My name is Erik Mosekilde. I'm a professor in physics at the Technical University of Denmark. The idea is to try to understand the complexity we meet in the living systems. Many of these systems can be described in terms of dynamical system theory. That means the theory of feedback regulation, stability, self-sustained oscillations, synchronization, etc. The so-called flow diagrams that we are trying to use in this course here provides a one-to-one representation of the equation of motion. Boxes represent stock or state variables. That means accumulations of physical or chemical entities, different types, such as, for instance, the amount of insulin in the blood compartment. Valves represent flow variables, and together the stock and flow variables define the conservation conditions of the model. Let us try to see how this works out in practice. The first slide shows the absorption curves, so-called absorption curves, for 7 patients with diabetes. They have been injected with insulin, so-called 4 international milliliters soluble insulin, with an amount of 0.2 milliliters. The insulin has been radioactively marked so that you can measure from the outside with so-called scintillation counter. You can measure how much insulin is still back in the depot for the individual patient. The different crosses and points here show the 7 individual patients, but this is not the interesting part of this thing. The interesting part is that the absorption curve is not linear. It's not a straight line in this plot where we have the percentage remaining insulin as a function of time up to about 8 hours or something like that. The fact that it's not a linear development here can be supported by the fact that in a linear system it will always be so that different modes separate from one another. They don't depend on one another. They can be separated, and this shows up in the fact that the fast mode always will be the first to play out, and the slow mode will come later. But in this particular case, we see that the slow absorption rate is first, and then the fast absorption rate comes later. This must mean in some way that the interactions here, that the processes involved in this system here are nonlinear. Christian Binder, who did these experiments that we have just seen, also did a more detailed analysis of what happens as the concentration of injected insulin goes down from 40 international units per milliliter to first 4 international units per milliliter, and thereafter to 0.4 international units per milliliter, altogether 2 factors of 10 or factor of 100. And he also looked at what happened as the injected volume goes down to 0.1 milliliter and to 0.01 milliliter here. And the strange thing is that both the injection concentration and the injection volume affects the absorption curves. The picture that we have tried to derive from this is that actually the insulin occurs in 2 different forms depending on the concentration of the insulin solution. If the concentration is relatively small, insulin is on a so-called dimeric form. Dimeric form means that the insulin molecules are bound together 2 and 2, dimer 2 together, and at higher concentrations the insulin is on a hexameric form where you have 6 insulin molecules bound together. Now, insulin is a sort of peptide protein transition molecule that has difficulties in passing the membrane between the blood and the interstitial region And the result is that while the dimeric insulin can pass this, the hexameric insulin cannot pass it. And the idea of interpretation, this particular figure here, is then that in the beginning the insulin concentration is so high that a large part of the insulin is on a hexameric form, and therefore the absorption is slow. And as the insulin in the depot becomes less highly concentrated, the insulin becomes dimeric and has a faster absorption rate. This picture also fits to these results here, but as you see, when the volume becomes sufficiently small, then there's another effect. Now all of the absorption more or less becomes rapid, and the idea is here that this volume is so small that the concentration is thinned out because of diffusion of insulin in the tissue, and the result is that the absorption becomes faster. Also here you see the faster absorption. Now it's because the insulin is a slower concentration from the very beginning. There's not much of the slow initial absorption, and here. And what happens if the concentration becomes sufficiently small and at the same time the amount injected insulin becomes small, is that it develops a region of slow absorption up here, where our interpretation is that insulin must occur in a different form. Our assumption is that it's in a bound form, where there may be sites in the tissue into which the insulin can bind and is only released slowly. The interesting note is perhaps that many of these experiments are performed outside of the normal pharmacological regime. That means that most people have never thought about doing experiments in this region to try to understand what happens up here also. The most important challenge in biosimulation is, of course, to try to set up models of the various biological phenomena that we study. However, we have already interpreted now the different curves of insulin absorption, and it would be more interesting to try to see how we can set up a mathematical model of the same processes. And this will be the next slide. So the idea that we try to proceed with in the discussion of the absorption of insulin from the skin is that we have in principle 3 different insulin forms that can enter the system. We have hexameric insulin, where 6 molecules are bound together. We have dimeric insulin, where 2 insulin molecules are bound together. And then we have a state in which insulin is bound to other things, proteins or whatever, in the tissue. And what happens as you reduce the total amount of insulin in the injection site is that you actually shift the relative significance of the different forms of insulin. In the flow diagram, we can follow here that there's a transition between dimeric and hexameric insulin. It shifts so that as the insulin concentration becomes higher, there will be more hexameric insulin and less dimeric insulin. And there's again a balance between bound insulin and dimeric insulin. If the dimeric insulin is sufficiently high, it will override the bound insulin. But if the dimeric insulin the concentration of dimeric insulin becomes very low, then the result will be that all the insulin will be bound and nothing will be absorbed. These are the absorption rates of the dimeric insulin. This cannot absorb, and this cannot diffuse in a tissue because it's bound to sites. These 2 forms of insulin can diffuse in a tissue, and this is where the concentration comes in. Let us try to understand these equations of motion, which are actually simple laws of mass action as they are known from the chemical region. So we have 3 different forms of insulin: dimeric insulin, hexameric insulin, and bound insulin. If we start with the bound insulin will be increasing, removed from the bound states at a rate which is the concentration divided by the binding time. It will be bound at a rate which is the product of the actual concentration of dynamic insulin and then the number of free binding sites. And the number of free binding sites is the capacity, binding capacity, minus the sites that are already been used, bound. And then there's a rate factor in front of it that determines how fast this process will develop. In this equation, now we have hexameric insulin. It diffuses in the tissue, so we have a diffusion constant, and then we have Planck's constant, or Nabla squared, times the concentration here of hexameric insulin. And it also has a transition between dimeric and hexameric insulin, and this is determined by this law of mass action that says that you need to have free dimeric insulin transformed into one hexameric insulin. And the result is that in this chemical process you need to have a power of free in the dimeric insulin concentration. And on the top here we have all the different processes together. The dimeric insulin takes part in the binding process. It's just the negative value of the binding rate for the bound insulin. The dimeric insulin takes place in the exchange with the hexameric insulin. This is again with just the opposite sign. Dimeric insulin diffuses in the tissue, and this is assumed now to have the same diffusion constant as the hexameric insulin. And finally, as the only of the free versions of insulin that can be absorbed, we have the dimeric insulin, which is absorbed directly from the tissue and into the blood vessel at the injection point. The next slide shows the simulation results, the different absorption curves that we obtain depending on whether we have 40 international units per milliliter or we have 4 or 0.4 international units per milliliter, and depending on how much water we have. And we have understood that the general picture is now that the amount of insulin in the beginning is so high up here that a measurable fraction will be on a hexameric form. The hexameric form will not diffuse into the blood vessels, and the result is that the absorption rate is relatively low here and then becomes higher as we reduce the concentration as more and more insulin moves into the blood vessel. If the amount of insulin that we inject is smaller, then in the beginning there will not be much different, but the transition to the fast absorption will be faster because insulin solution diffuses faster into the surrounding area. So this is an effect of the diffusion in the tissue. And the same as here, we see the diffusion is now so fast that it's almost hexameric insulin altogether, all the way, in spite of the fact that we inject also hexameric insulin up here. And the same with these curves, we see how the slow final absorption rate comes in here as we use concentrations that are very low here, and the number of bindings are sufficient to bind most of the insulin. So the result is that these curves here that we calculate actually identify the different parameters one by one if we consider the process as we just described it here. This is the dimeric absorption rate that is given by the slope here. The hexameric is not absorbed, so it's a fraction of insulin which is back on dimeric form that determines this curve here. And the fraction of insulin which is still there on dimeric form at high concentration determines the equilibrium constant between hexameric and dimeric insulin. As you increase or reduce the concentration, there will be more and more significance of the binding states. This is, as we said before, maybe the rate of this curve determines the relief or the binding time of the insulin to the different sites where it can bind in the tissue. And if you go back along this line here, we find actually the concentration of bound states in the system. So all the parameters can be sort of identified from these curves here. The next slide shows the simulation results, or some of the simulation results. In particular, the idea is here to show that we can use a model to follow curves or behaviors in the system that we may not be able to see in the experiment. Here we have plotted the hexameric as a function of time, the hexameric concentration of hexameric insulin or residual insulin of hexameric form here as a function of time for 8 hours. And you see in the beginning all the insulin is almost at hexameric form. The result is that the absorption rate is fairly slow. During this period here, the dynamic insulin is being absorbed, but it's renewed again by the decreasing hexameric insulin. So the hexameric is transformed into dimeric, and the dimeric is absorbed, and this continues until the hexameric curve falls below the dimeric curve. Then the dimeric insulin also starts to be absorbed at a much lower rate until it finally dies out. But in this region here, the dimeric insulin is almost all of the insulin, and that means that here we have an absorption constant which is defined in terms of the dimeric absorption, and up here we had an absorption rate which was determined by the fraction of dimeric insulin times the dimeric insulin absorption constant. And this finally curve shows the fraction of dimeric insulin that we have in the system. So it increases in the beginning. Most of the insulin was in hexameric form. As they cross out there, the insulin is now dominated by dimeric, but it doesn't reach up to be 100%. It's only something like 80% is the maximum in dimeric form that we have. So one can say, if we wish, that the model allows us to check whether there's a consistency in the internal behavior of different variables that we can't measure directly. The next slide shows how, by introducing plasma and intercellular spaces, the model can be extended to describe the appearance of insulin in the blood, the appearance of insulin in the intercellular liquid, and the rates of insulin degradation from the two level variables, the hepatic degradation together with renal degradation, and the muscle and adipose tissue degradations. Yeah. The way to measure the hepatic insulin degradation is to measure the incoming blood flow to the liver, the outgoing blood flow to the liver, and the concentrations of insulin in both flows, together with the total amount of blood flow. Then you can calculate that the insulin absorption in the insulin degradation in the plasma typically has a lifetime of 5, 6, 7, 8 minutes or something like that. The lifetime of insulin in the intercellular liquid is sufficiently longer, and the result is that it doesn't influence the overall lifetime much. So with these two additions, we can calculate the appearance curve from the absorption curve, and we can now compare the appearance curve with experimental results here. It's obvious for us that the experimental results should have been made with a higher frequency and with more accuracy in the actual plasma insulin concentrations. But this is one of the things that you often learn when you start to do models, that the experimental conditions are not optimal for doing the conclusions that we want to draw. The next slide shows what happens as insulin concentration in the injection insulin increases. The classical insulins, they have concentration of about 40 international units per milliliter. Today it's more common to use insulin with a concentration of 100 international units per milliliter. Here we have compared the model predictions with the original data or parameters for the 40 international units per milliliter and 100 international units per milliliter curves. And we can see that the original predictions hold quite well, but also that the higher insulin concentration as predicted by the model results in a slower absorption from the depot. That means that you get a lower maximum and a longer tail after the maximum has been reached of the insulin concentration in the blood. This is then for the 40 international units per milliliter, and the red curve is for the 100 international units per milliliter. For even higher concentrations of insulin, one must expect that the absorption delay becomes even longer. This figure shows a comparison between the appearance curves for two different concentrations of insulin, 100 milliliter per 100 international units per milliliter and 40 international units per milliliter. And it shows that there's no dose linearity and there's no bioequivalence between the same dose administered with different concentrations. The area under the curve is nearly the same for the two simulations, but the ratio between the Cmax values, the maximum values, is slightly larger than the factor of 1.25 prescribed by the European Medicines Agency. The idea of microdosing is to reduce the number of animal experiments by adopting a first-in-man strategy in the drug development process and by using initial doses that are thousands of times smaller than the anticipated active dose. But as we have seen with insulin, if there's a binding possibility in the tissue, then if you go down in the concentration of the drug to below a certain level, then all the drug will actually bind in the tissue and the release will be determined by the release rate from the binding site. And only when you cross above this threshold will the dynamic insulin start to produce absorption directly. An interesting problem would of course be to know what will happen as the concentration of the insulin is even further increased. We have looked at 100 international units per milliliter and 40 international units per milliliter, but to improve the treatment of patients with very extreme insulin resistance, one could think that perhaps one should use insulin with a much higher concentration, for instance, as suggested here, 500 international units per milliliter. But on the basis of the model, we have suggested that insulin of higher concentration than the 40 international unit per milliliter actually absorbs slower than the 100 international unit per milliliter insulin. And if you go to 500 international units per insulin, the absorption of insulin becomes so slow that it is actually as if you are using the so-called MPH insulin, which is a crystalline form of insulin that has a much lower absorption rate. The objective of replacing insulin bolus injections by smaller and more frequent infusions from an insulin pump is to maintain a more constant and better regulated plasma insulin concentration. And this is a direction that most modern use of insulin or treatment of diabetics develop. Considering that the lifetime of insulin in the blood is as short as maybe 6 minutes, it's of course a basic question, how fast should one actually pump the insulin from an insulin pump. And again, this was dealt with in the model some 30 years ago, and the result was that due to the build-up of a depot under the skin, there was a sort of smoothing out of the insulin concentration in the blood plasma, and the result was that one could operate with 1 pulse per hour or something like that, and still get variation in the insulin concentration in the blood of a fraction, a few percents.